All right, so let's put everything together and understand how prime numbers, how the ideals that they generate, are going to factor in cyclotomic fields. We did this. We had a complete description for quadratic fields before, but now our other family of fields that we study or that we care about are cyclotomic fields, and we'll do it in this case. So this is called the decomposition theorem for cyclotomic fields, and let me start by stating the theorem. So this is theorem 3.6.13, and what does it say? So I guess this is called a decomposition theorem for cyclo fields. So that's the title of this section suggests. So what's the theorem? So this is going to be a full generality. So I'm going to let n be an integer, and z to n, it's very bad, z to n, I can always, when I write z to n, I mean primitive, nth root of unity. I'm going to let k be the relevant cyclotomic field, so k z to n, so qz to n, and I'm going to take p a prime number. So how am I going to understand how what I wanted to say is I want to say how this prime number p, how the ideal it generates, looks like in this field. So this case is actually quite a nice description. So first of all, we start by writing, take your n, which is what your root of unity is, and factor it as p to the k times m, where p doesn't divide m. So find how many times p divides the number n that you care about. And I'm going to set e to be phi of p to the k, where phi is the usual Euler tangent function. Phi being Euler's tangent function. So counts how many numbers less than n are co-prime to it. So how many numbers less than p to the k are co-prime to p to the k. And lastly, so this is going to turn out to be my ramification degree. Lastly, I'm going to let f be the multiplicative order of p, of my prime number p, modulo m, so i.e. p in z mod mz star. So this is a group. Figure out what order p has in this multiplicative group. That's what f is. So when we have these two numbers, then the theorem says that the ideal generated by p in OK, let's just be precise. This looks like p1 to some pr to some conductor, so to some power e, where e is going to be the, as is obvious from this is going to be the ramification degree for any pi, and f, this number that I defined here to be the order of this f, which is the multiplicative order of p, is going to be the common, they're all going to have the same residue degree, and this f is going to be the residue degree of this. So we've saw before that in a cyclotomic field, the ramification degree was always the same for all the primes, and they all had the same residue degree, because we knew this field was normal, so this happened. But what this theorem is telling you is how to find what e is. E is just, you use it by finding what phi of p to the k is, so this depends on that, and f is just the order of multiplicative order. So this makes it really simple. You just have to do it's very simple like group theory, and then you can figure out. It won't tell you what these pi's are, but it tells you what the structure is, what the ramification, what these pi's look like. So it's not as good as the previous theorem, which told us explicitly how to construct these pi's, but you could do this. You could go back and use like the Decomposition theorem to try and figure out what these pi's explicitly are. And once you know what all of this structure, it should help you a lot. So for the proof, we're actually going to have to use two different lemmas to prove this, to somehow split up the proof. But I'm going to start by splitting things up a little bit. So I'm going to let alpha be zeta n to the power m, and I'm going to let beta be this my root of unity to the power p to the k. So this means, if you think about this means that alpha is a p to the kth root of unity, and beta is an mth root of unity. So we're going to prove the theorem by looking at how p factorizes in the fields that alpha and beta generate. By seeing how p factorizes q alpha and q beta. Well, obviously, what I mean is in the rings of integers, not in the field, but in the rings of integers. So to do this, let's start with a lemma. So here's the first one is a bit easy, or easier. So this lemma 3.6.14. So with the above notation, in Q alpha, we have that the ideal generated by P looks like 1 minus alpha to some power, and this power is phi p to the k, that number e that I wrote down, with, just to make it clear, 1 minus alpha, a prime ideal. Notice that normally we would call alpha something like zeta p to the k, because I said it's a p to the k root of unity. In which case, 1 minus alpha is like this lambda p to the k. Yeah. So note, let's say note. This is a p to the k root of unity, so 1 minus alpha. This is what I would call lambda zeta p to the k in our previous notation. And we somehow checked that this element had norm p, which somehow means that this ideal has to be norm p, which tells us that this ideal is going to be prime. This is just a note on notation. So alpha is a p to the k root of unity, so normally we'd denote it by like this. I just somehow wanted to simplify my notation. So let's prove this. So prove this lemma. Proof. Note that the first thing is note that we know that degree. So note that this degree of q alpha to q, this is degree of some cyclotomic field. We know that this is where the Euler tangent function comes in. So we know that this degree is phi to p to the k. Since this is the degree of the cyclotomic polynomial, I'll just say C lemma 2.3.1 for this. Now, one of the exercises that I left in the notes for you to do, but it's fine if you haven't done it. So, but next, by exercise 2.3.6, we know that the prime number p can be written as, in this field, we can write it as u times 1 minus alpha to the phi p to the k, for u a unit. So this is a unit. And I guess in this ring of integers, O, Q, alpha. Oh, we actually know what this is, right? We know that this ring is, I'll just, O. Although I only proved this in one case, but I gave you the theorem in general. I told you that for cyclotomic fields, the rings of integers were always like Z alpha, where alpha was this obvious root. But anyway, we know that P looks like this with P a unit. So this implies that as ideals, we get P is 1 minus alpha phi p to the k. And theorem 3.5.7 then gives the result. By which I mean, this theorem told us a relationship between the ramification degrees, the residue degrees, and the degree of the field. In this case, I've checked that this looks like a bunch of products of prime ideals, and I've not missed anything because this is the degree of the field, so this is actually totally ramified. So this, each of these is a prime. Each of these is a prime ideal because, well, if you guys go back and look at these alpha these lambda p's, or in one of the exercises in sheet 5, I guess, the hard one. This thing has norm some power p or p, so this is you can check this the prime ideal. Okay, so we somehow understand how the ideal p factors in this field in Q alpha. Now I want to do the same thing for Q beta. So here's the other lemma, 3.6.15. It says in Q beta, P is unramified, and for each prime ideal P dividing P, we have this residue degree equals to F, which is F was the number in my statement of my theorem, was this degree of the multiplicative order of the P mod. I should say here, prime ideal. Okay, so this one's a little bit harder to prove, so proof. So start by using corollary 3.6.10, which told us about, let's go back and show you it. This corollary here, which said that if I have some polynomial, some root of some polynomial, and P didn't divide this norm of the derivative of alpha, then P had to be unramified. So I'm going to use this corollary to check that the first statement that the prime is unramified. So using this with, so I don't really want to write down what the minimal polynomial of beta is. I don't really know what it is, but I know that it's a mth root of unity. So I know that one polynomial satisfies with f of x equal to x to the m minus 1. I'm going to say note beta is what we would call zeta m, an mth root of unity. So using this corollary, we need to check if P divides the following quantity. So if you write it out, this is going to be m to the power of k of beta to k. This is just plugging in, I think, and then norm from q beta to q of beta to the m minus 1. Differentiate this polynomial, you're going to get m times x to the m minus 1. The m, if I take norm of that, then the m gets just raised to the power of a degree of the field, and then you get the norm of this at alpha, at beta, because it's what I'm plugging in. So I end up having to look at this number. I'm going to check if P divides this. But by construction, P doesn't divide m. Remember that I took my prime number, I took my number n, and I factored it as P to the k times m, where P doesn't divide m. So I know that P doesn't divide m, so it doesn't divide this factor. It's got to check if it doesn't divide this factor. And beta is a unit, it's a root of unity, so it's, in particular it's a unit. It's a unit, so its norm is plus or minus 1. So this number is plus or minus 1 to some power. So, and this is just not divisible by P, so we get that P is unramified. Therefore, P is unramified. So what do we know? Because it's unramified, we know that the factorization has a little bit of a factorization already. So in O Q of beta, which again, because this is a cyclotomic field, this is just Z of beta. We have, what do we have? We have this prime ideal, whatever it factors are, is going to have factors like this, P1 to PS. So we're going to have some number of factors, don't know how many, let's call it S, but they're all going to be distinct, and there's going to be no powers showing up because it's unramified, so there's no powers showing up. So that's the first thing I know once I know it's unramified. So now let's try and figure out something about the residue degrees. This is a bit, I guess, a bit more difficult. So, moreover, since this is a cyclotomic field, since we know that Q of beta over Q is normal, it's a normal field, we know that f of pi to p is the same as, say, f of pj to p for all I and j, because in normal fields the residue degrees always stay the same. So I'm going to just give a name for the first prime. So I'm going to let just p be p1. I just need to check, so these are all the same. I need to check that one of these is this number f, the multiplicative order of p mod m. So we need to check that this residue degree equals f. Cool. So remember this, yeah, f is a multiplicative order. So let's start on this. So I'm gonna do some more notation. So I'm gonna let f square p, so f goth p, be the residue field. So this is z beta mod p. Recall that. Go back and look at the definitions of residue fields. If you're confused with one constant residue field, recall that by definition we have that this degree is going to be the degree of f square p to just f p, the base field. So we know that this, whatever this number is, I'm going to call this, I'm just going to ease my notation, I'm going to call this h. So this degree is whatever this degree thing here is. Here's some h. We want to show h equals f, and we're going to just do this in two steps. We're going to show first h is less than or equal to f, and then the h is greater than or equal to f, and then we'll get equality. So we do this in two steps. So the first step is h is greater than or equal to f. So we need to let's check this this part of the claim. So I'm going to use this residue field. So remember that this is the ring of integers, and of course you know my prime ideal. Prime ideals and all these things are maximal. So this is actually a field. So this is actually a field extension over fp, because this is fp is a prime over p. So this is some degree field. So this is some field of order p to the something, p to the h in particular. So first of all, I'm going to let beta bar denote the image of beta in this fp. So I'm going to let this denote the image beta in f square p, f ideal p. First show that as an element of this field, or it's multiplicative, it has a multiplicative order. We're going to check that beta bar has order m in this field. So multiplicative order. So assuming this is not the case, assume we're not have the case, then beta to the so if this isn't the order, then beta bar to the m over L is congruent to 1 mod my prime ideal. So in here in this thing, so looking at congruent elements in here is the same as when we talk about things being mod something else. So the order is going to be smaller, so it's going to be some m divided by L. For some prime factor L dividing m, whatever it is. Notice that, yeah, this is the mth, this field, that this is the ring of integers in the mth cyclotomic field. So this isn't just a random m. So now, what does this mean? This means that beta to the m over L is an Lth root of unity, This is the order mod p, so this is some L through divinity. So by one of the previous exercises, so by, what is it, exercise 2.3.6, just again one of these exercises about cyclotomic fields which I left in the notes, we see that this is the same exercise used above. Beta to the m over L minus 1 divides L. It's a analogous result. This result that I used here, this result here, is analogous, works for any root, any cyclotomic field. So it's the same thing. I have 1 minus beta and I have L in this case because I'm talking about L through divinity. So this divides L, and L is a factor of M. I told you that L divides M. Therefore, my prime ideal P divides M. So I just, this means that this minus 1 is divisible, is 0 mod P. So this P divides this thing, and L divides this thing. So somehow you put them together and you get this. But this is a contradiction. Gives a contradiction. This prime ideal P divides P, and the GCD of P and M by construction is 1. So this can't have happened. So this beta has to have order M inside this field. So that's basically the biggest order. Great. So this has order M in here. So by Lagrange, this theorem, that means that if it has order M, it divides the order of the group. So this means M divides the order of the group. What's the order of the group? Well, this is the norm of P minus 1. And then this in this field here, right? In this case, this thing here. So M divides the size of this thing, which is the norm of P minus 1. And note that since P is a prime ideal, we know that the norms of prime ideals are always powers of prime. So we know the norm of P is, we know what the residue degree, but we know what this, I gave a number to this. I know that H is the residue degree, so of P. So we know that this is actually, the norm of this thing is P to the H. Therefore, so I know that M divides P to the H minus 1. So this means that P to the H is congruent to 1 mod M. But the order of P mod M, this is the number F I have, is F. So I know that F has to divide H, i.e. H is greater than or equal to M. Right? F was defined to be the order of P mod M, and I know that P to the H is 1 mod M. So whatever F is, it has to be some number dividing H. And so in particular, H has to be bigger than F. So this gives me the first direction, and I'm just going to do the second one. So now we do H has to be less than or equal to F. Okay, so I want to do the second bit, that H is less than or equal to F. So we know that the following. So since we know that F is the order of P mod H, we know that since P to the F is congruent to 1 mod M, then what do we know? Then it follows that if you think of what this is, a beta is a P to the beta is a M through to unity. So this is beta P to the F equals beta, right? Beta is an M through to unity, so if I raise it to some power which is 1 mod M, then I stay back to the same thing. So p to the f is this. Now, note that by like Fresher's dream, you have like x plus y to the p to the f. This is congruent to x p to the f plus y p to the f mod p. Which means that for all gamma in my ring of integers, we have gamma to the p to the f is congruent to gamma mod mod p, but p is contained inside my prime ideal. P divides my prime ideal p, so this ideal is contained in this ideal p. So the same thing holds, but instead of mod p, but mod my prime ideal. So this is going to gamma mod my prime ideal p. Therefore, every element of fp satisfies, well, is a root of x to the p to the f minus x. This is what this is shown. Everything is satisfies a root of this in f. Wrong p. F square p. Remember, this was z beta over my prime ideal p. So everything is a root of this, but this is a field, and so I know in a field that a polynomial of degree p to the f has at most p to the f roots. So since fp is a field, we know x p to the f minus h has at most p to the f roots, and I've checked that every element in here actually is a root of this. So since fp has p to the h elements, by definition, we get p to the h has to be less than or equal to p to the f. We can't have more roots than we have degree of my polynomial, which implies h has to be less than or equal to f, which gives the result. Great. So now I'm going to combine both lemmas to get the full theorem. So, putting these lemmas together, get the theorem as follows. So, what is it? Using lemma 3.6.14, the first of these two that we proved, and the theorem 3.5.7, this one which related to degrees of the field to the ramification and residue degrees, we get that so that the ramification of 1 minus this over p, I told you this was a prime ideal, times the residue 1 minus alpha over p. This thing equals e times 1, which has to equal the degree of my field, which I know this is 5p to the k. This is the first theorem. Similarly, lemma 3.6.15 gives this case. Remember, in the first lemma, we only had we only had one prime ideal showing up in my factorization, and here I had whatever it was. I said that there was s prime. I was unramified, and there was s of them showing up. So in this tells me that what I have is s times whatever the ramification degree is times whatever the residue degree is. This is s times 1. It's unramified, so this is times f. S is the same. I checked that my prime was unramified, so all of these are 1. And I know that this residue degree is the same as this f, which is the multiplicative order of p mod m, and combine this with the result, which tells me the degree of the field. It tells me that this is this degree, which is, because this is q z to m. This is the degree of this field is maybe I'll stand here. This is q z to p to the k. The degree of cyclotomic fields, we know what they are, so these two degrees are this. So now I let, say, beta I be the prime ideals in my full ring zeta n over p. Then we know, what do we know? We know that the sum over I, this is what this theorem 3.5.7 tells me, that this beta I is over p times the product of these residue degrees. This thing is the degree of my field, which is phi of n, which in this case is the same as this 5p to the k, phi of n, because phi of m, because m and p to the k are co-prime. So if you use this and compare with the Tower law, so using this is not the Tower law, 3.5.6 together with this, together with the Tower law. So talking about the Tower law, the q zeta n to q, this degree, the same thing as let me just write down let me put this in the middle. My degree of my, I can factor this in two different ways. On this side I can write this as q zeta n to q alpha, and then q alpha to q. On the other hand, I can write this as q zeta n to q beta, and then q beta to q. Comparing both sides and using this, what we know here, we get the result. So combining these two things, we get that S times E times F, these numbers have to be this degree to Q, from which the result follows. All right, so we've proven this decomposition theorem for cyclotomic fields. Let me go back and reread the theorem and tell you what it was, because it's probably forgotten by now. It's been so long ago. Remember, so I took n to be some integer, and I took zeta n to be some primitive nth root of unity, and I wanted to take some prime number p and say, how does this factor into a cyclotomic field? So how do I do this? Well, I look at the number n, which is my field. I write it as p to the k times m, where p doesn't divide m. And then I just calculate these two numbers, e, which is the phi of p to the k, and f, which is the order of p mod m. And then immediately I get that the factorization looks like this. I don't know what these prime ideals are, but at least I know what their residue and what their ramification and residue degrees are. So let's do an example of this, so we can somehow see this in action. Sometimes, yeah, I think that's in notes to something called the Cycloatomic Reciprocity Law. Somehow it's like a generalization of the quadratic reciprocity law. Because for quadratic fields, remember we used quadratic reciprocity, and somehow we were using that to describe prime ideals factoring completely. And somehow this is a theorem which decomposes primes in cyclotomic fields. So maybe you want to call this the cyclotomic reciprocity law. Anyway, example. I'm gonna take k to be q zeta 5, and I've made some little tables to help understand how this looks. So I'm going to look at I'm going to completely describe how the primes look like depending on what p is mod 5. So I'm going to let p be a prime number, and so let's do a table. So here I have p mod 5, so it's going to be 0, 1, 2, 3, or 4. 0, 1, 2, 3, of 4. No. So the first is going to be the prime mod 5. Now I'm going to do the order of p mod 5. So these are my f's. So let me work this out. If p is 0 mod 5, then there's no order. There's no multiplicative order, so there's just nothing to think about. If p is 1 mod 5, then the order of that is 1. 2 mod 5, if you think of what the order is, 2 squared is 4, 2 cubed is 8, and then 2 to the 4 is 16, which is 1 mod 5, so this has order 4, this has order 4, and this 4 has order 2, 4 squared is 16, which is 1 mod 5. So I have my primes, mod 5, what their order is in the mod 5 there. And now here I'm going to tell you what the factorization is, of what this prime ideal is, just from knowing these two things, and figuring out the phi function. So in the first case, the ideal generated by p just it's totally ramified. It looks like some prime ideal to the power 4. 4, remember, is just phi of 5. So p is 0 mod 5. So p is a prime number. So p is 5, right? So in this case, if you go back to the theorem, I'm applying, so n equals 5 and p is 5. So when I write n as power of p times m is 1, p is this, so then e is the phi of 5, which is 4. So in the first case, we get that the ideal is totally ramified, and we get this. And I'm not sure what this p is, but I know that is the case. In the second case, these residue degrees are 1, and so if you work through this, you're gonna get 4 prime ideals above it, because we know that it's unramified, and we know that the residue degrees are always are the order of p mod 5. So all the residue degrees are 1. So in order for me to have this equality of, theorem 3.5.7 tells me that there has to be 4 different primes showing up. So it has to look like this. Similarly, in this case, this has to stay prime. So this is inert. Similar here, the residue degree is 4 in each case. So this is as big as it is, so the prime has to be inert. And the last one, well, the prime ideal has to split into 2 factors. So p1 and a p2. And we also get because we know what the residue degrees are, we get the norms of these ideals as well. So the norms, what do we have? We have, in the first case, we have the norm of this ideal p, it's going to be p. In the second case, norm of each of these pi, again, the residue degrees in each of the cases is 1, so this is going to be p to the 1. Here, the norm of this ideal is prime, so it stays the same. In this case, it's going to be p to the 4. 4 is the residue degree, so it's this number here. It's p to this number here, apart from in the first case, because it doesn't really make sense in the first case. Again, norm of p is p to the 4 here, and here the norm of these pi's is p squared, because it's 2 here. So although we don't really know exactly what these pi's are, we know what the ramification degree is, residue degrees, and we know all their orders. And you can somehow use this to actually just move up. So I just in qz to 5, but now if I just move up to qz to 55, then you'll get similar. You can somehow build up your results. So we can go further and look at, for example, q zeta 55, for example. Over q zeta 5, and you can check that. In this case, what do you get? You get that, for example, the prime ideal 11. This is going to factor as p1, p2, p3, p4 to the 10th. So maybe I want to write over q here. But if you build up from qz to 5 up to qz to 55, so you multiply by 11, you can use this factorization to somehow build up and prove things like this. With, in this case, the residue degrees being 1. So yeah, you can play around with this, try other primes. I think one of the exercises on the sheets will be doing it for 7. But we can now give a very good description of what primes look like in cyclotomic fields, or how they factor. It's quite satisfactory. Great. So this ends our second chapter, our third chapter. And next time we're going to start talking about the class groups and somehow seeing how I said I can make a group out of these ideals in a number field. We're going to study this group and figure out the size of it and what it looks like. But